Hi. All right, so in this video, we're going to start talking about angular momentum and rotational spectroscopy for the first time. So it should be no surprise to you by this point that angular momentum and rotational spectroscopy are both have really important and distinctive quantum characteristics that make them behave very differently than you would expect from classical systems. You can probably expect this because we're talking about it. Otherwise, we'd probably just skip it. Right? And so when we think about angular momentum, what we should be thinking about is a molecule tumbling in space. So this can either just be a diatomic molecule, like sitting there. It could be something like N2 tumbling in space, or CO2. Okay, so what we think about is we want to understand the quantum motion of how this molecule will sort of rotate and tumble in space. For most of this section, we're going to be mostly interested in linear molecules like N2 or CO2, but a lot of the same concepts will pop up even when you're dealing with polyatomic molecules. It's just that the math is more difficult. Okay, so to get us started, we need to think about what an angular motion looks like. And the way we should think about that at the start, if we look over here, is in the system, we have two masses. This is mass 1 and mass 2 that are both rotating about their center of mass. And the center of mass, will sit somewhere between them, slightly closer to mass 2 than mass 1 if it's bigger, the way it's shown here. Okay, and so they're both going to rotate around this center of mass point. And we're going to call the distance between the center of mass and mass 1 or M1, that's called L1, and then the distance between M2 and the center of mass is called L2. Okay, and so this is everything we need to define the system, or this system of spinning or this spinning molecule. Okay, so first off, what we want to do is to figure out what the energy would be involved in this angular motion. Let's start out thinking about this classically. So first, we're going to imagine that whatever the system is, this is tightly fixed. We're going to imagine that it is rotating with some overall frequency nu, right? So so nu has units of 1 over a second, let's say. And so what nu is telling us is that, blank number of times per second, this M1 will do a full rotation all around at the same time that N2 will do a full rotation the other way around, okay? Or in the same direction. Okay, so what we want to do is we take this linear frequency and we want to turn this into something that tells us some information about the velocity, right? And so we're going to do this separately because the velocities for M1 and M2 could be different. Okay, so for particle 1, we have V1. And the distance that it's traveling is going to be 2 pi times L1, right? And so what this means is that this is moving one rotation around every time, and the distance is traveled during this whole rotation is the circumference of the circle with radius L1, and that's 2 pi L1. So what we have is it's making nu of these rotations every second, or in other words, it takes 1 divided by nu seconds in order to do this. Okay, so if we put this together, this means that V1, the velocity that particle 1 is moving, is 2 pi L1 nu. And if we apply the same logic for V2, the only thing that changes is that now V2 is moving around a slightly different distance away from the center of mass because it is heavier. And so in this case, we have 2 pi L2 nu, right? But it's the same frequency. And so that part doesn't change at all. Okay, and so now what we'll do is we're going to group this 2 pi and this nu together, and we're going to call these the angular frequency. So this is omega is equal to 2 pi nu. This is known as the angular frequency. Okay, so now we can rewrite this as V1 is equal to omega L1, and V2 is equal to omega L2. Okay, so what can we do with this? So now what we do is remember that the kinetic energy for a set of two particles, let's call it T, is equal to the sum of the kinetic energies of the individual particles. So it's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And if we plug in what we just derived for v1 and v2, then we have 1/2 m1 L1 squared omega squared plus 1/2 m2 L2 squared omega squared. Okay, now we're going to rewrite this in a slightly different way. So we're going to just group some things. Write this as 1/2, and we do m1 L1 squared plus m2 L2 squared times omega squared. And now we make a definition. So this term here, which is the m1 L1 squared plus m2 L2 squared, this we're going to call I, which is the moment of inertia. And we'll talk in a second about what that means. Okay, so now in terms of I, this equation becomes 1/2 I omega squared. Okay, and part of the reason we do this is that now we can draw an analogy with the way this looks and the way that the normal kinetic energy looks. So if we compare these different parts, we have here I and M look kind of similar, and the omega squared resembles V squared. So what we've done when we define the moment of inertia is that this is really, the moment of inertia is really kind of the closest thing to an analog for mass in a rotating system, right? And what makes it different is that now the length for this comes in. And so this is sort of a closer analog. And then similarly for the velocity, instead of it being a raw velocity, what we have is this angular frequency. And again, these are both very different, right? Because for one, they have different units. The angular frequency only has units of time, whereas the normal velocity is, time, distance per time, and the moment of inertia has that distance in there. But it does allow us to write an equation that is really reminiscent of this mv squared. We just have to now change it to I omega squared. Okay, and the final thing that helps simplify this, it turns out for this system, the moment of inertia here can be written as mu L squared, where mu is the normal reduced mass that we're used to, the same one we saw with the harmonic oscillator problem, and L is the total bond distance. Which is the sum of L1 and L2. Okay, let's make one more definition to really draw out this analogy between linear momentum and angular momentum. Right, and what we're going to do is define this thing called angular momentum, which is L is equal to I omega, right? So if we're drawing a connection between mass and the moment of inertia, and also a connection between the velocity and the angular momentum, or then the angular frequency, then this kind of makes sense to be a momentum, right? Because this looks kind of like, so this part looks kind of like the mass, and this part looks kind of like the velocity, and mass times velocity is momentum. And so this, okay, so L equals I omega is the angular momentum. Now we can once again use this to write the kinetic energy in a way that's more used to what we've been doing in this class, and that would look like this. Which is totally equivalent. Okay, and in the rigid rotator model, we're going to greatly simplify this whole idea by assuming that the distance between these two particles is fixed, right? And so in this case then, the Hamiltonian that corresponds to just the rotation of this rigid rotator, right? So we're not allowing for any vibrations or anything like that. The part that just corresponds to the overall rotation will have an operator form now. The quantum mechanical operator form, looking in the middle, will look like this. So we'll write it as L squared over 2I. And this is going to, so this is the kinetic energy, and this is going to look like minus h bar squared over 2I del squared. But importantly, with a fixed distance. And this fixed distance is an added complication. And it turns out that the easiest way to incorporate this added complication is to switch, instead of working with Cartesian coordinates, to start working with what are known as spherical coordinates, which hopefully you remember from some work in calculus previously, but we're going to talk about in the next video.